with this formula for what I'm calling the posterior predictive distribution. I'd like to talk about that formula for a couple minutes. And then I want to just kind of show you on the chalkboard how you can work through this formula. Sometimes you can actually work the integral and write down in closed form expressions what the distribution is. We'll look at a couple examples. I'll probably come in with the integral on the board next time for the normal example, so you can at least see it once, you know, in all the steps. So I'll detail it all. I used to do that in class, so if you want to see it in advance, you can watch me do it in real time. I mostly choose not to do that anymore. So long integrals, but we do that in review sessions. So if you want to see like off the cuff, all the hand details, review sessions are a really good time for that. I want to show you Monte Carlo approximations to this integral. So if you're familiar with Monte Carlo, you're staring at that thing and saying, sweet. If I know how to sample from this and from that, this is an easy integral to solve. And I'll say what that means. So basically you can do auto-integration by doing Monte Carlo. We'll see what that looks like. We need to think about what this formula is actually expressing to us first. And then I want to remind you what the iterated forms of expectation and variance are. And so those iterated forms are very useful when you have hierarchical representations of things. So I'd say there's a hierarchical representation. If you're trying to think about what the distribution on x tilde is, you would maybe sample a theta, then put that theta in here and sample x tilde out of that. And so if you wanted to move through the hierarchy, that's actually auto-integrating out theta as well, if you just throw it away and never look at it. We'll talk about that. But I want to point out also, there's something the book calls the predictive distribution. So the predictive distribution, and some people will call it this. It's just this thing. So if you write down f of x, and I can throw the tilde over here, use any variable that I want. I'm just going to write it down like this. So this will be f of x given theta, and you integrate with respect to the prior distribution. You integrate over everything. I usually call this the marginal distribution. The margin for x. So we've marginalized, we've averaged out theta. I don't use that terminology, the predictive distribution, because it's not like an informed predictive distribution. There's no data in there. And so it's just the marginal distribution of x. So I wouldn't predict using this because everything would be driven by my prior assumptions. So of course, if you knew something, maybe you could use that for prediction. Usually what people want to do is they want to integrate with respect to the posterior distribution. So that's all your knowledge about theta given the x's that you've observed. So these x's are coming from, so that's just your collection of x's. Your xi's are coming from this model. So the sampling distribution, as we always presume. So the data came from somewhere. It's got some structured randomness. That structured randomness is modeled by f. How do you get the posterior distribution? You just do the typical thing where you take the likelihood and you multiply it by the prior. So if you'd like to normalize it, you could do that as well. Very common to just write down what models are without their normalizing constants. So you just get the posterior distribution, plug that thing in. So let's just talk about this formula for a second. Again, what I said before is if you knew theta perfectly, you would just sample from the sampling distribution, and that's the best you could predict. So regions where there's a lot of mass, you would have a sample there more often than regions in the tails. And so if you're thinking about something like roulette at if you go to Vegas or Atlantic City or something like that, that's that game that you spin the wheel and there's a ball in there and it either lands on a black or red or a green. So, never seen any other colors. So that thing, you know what theta is. Presumably you think the ball is random. So it's just uniformly distributed into any one of those slots on any one of these numbers. And so seeing data doesn't really help you. You know what the distribution of the next draw is going to be. And so there's supposed to be IID, that is, the person spinning the wheel does it the same every single time, and they spin it in such a way that the ball falls into the slots uniformly. I don't know if that's actually true. I don't know anybody that's ever run a roulette table, and I would guess maybe there's something that's non-uniform about it. And so maybe each individual has their own probability distributions. They put a little twist on it or something like that. So as an example, if you flip coins, I doubt you flip it in a 50-50 manner if you catch it in the air. So if you let it hit the ground, then it's probably pretty close to 50-50. So anyway. So the data doesn't actually help you to predict there. So you're always going to have some uncertainty in your predictions, and that uncertainty is inherent to the sampling distribution. So what we'd like to do is plug in a good theta, but if we don't know a good theta, what we're going to do is average across thetas. So that's what this integral represents, is a weighted average. So it's a weighted average of this distribution with respect to these sampling weights. So keep in mind, we're assuming we've got a posterior proper posterior distribution. If you don't have a proper posterior distribution, you shouldn't be doing any of this. So those are sampling weights. So this really is just a weighted average of that function right here. And it's kind of the right thing to do. And what I like about this is it gives us a formula that we can always follow for doing prediction. Now, of course, the likelihood function has all the information about theta given the data, and this is something else that's regularizing the space, presumably. Hopefully you picked it for good reasons. One of the nice things is if you pick that distribution and it's not a very good choice, if you have a lot of data, it will overwhelm that prior. The likelihood will start peaking, and if you've used diffused prior beliefs, those will get drowned out relatively quickly. We'll talk about more details, more mathematical ways to think about that later. So I think this is the right thing to do. So if you weren't a Bayesian, what you might be doing is you might think, well, I'm going to come up with my best estimator for theta hat, so maybe the NLE or something like that. So maybe you think theta is close to that, so this is a point estimator. And what you might do if you're really lazy is build your prediction doing this. You pick your best guess and you just throw it in there. So it seems very similar. And if this distribution was very, very peaky around the MLE or something like that, so you had a lot of data, then it would be doing something very similar to this. But the Bayesian wants to express all their uncertainty about things as well. And so that's where the Bayesian really is winning in forecasting, is they're averaging over their uncertainties and they're quantifying them. And so people, I think humans, they kind of like you to say, oh, I'm 90% sure, or whatever, and like, I'm really sure about this. And you've seen that before if you've ever followed like the New York Times when they're predicting elections, they tend to be overly sure. So personally, I don't like that. I like to express the uncertainty, even if it's like, we're not really gonna be able to tell what happens here. So I understand that that might not feel good as somebody coming to a statistician and you're like, I think the next draw could be anywhere between almost negative infinity and infinity. So I don't really know very much about everything. And that would happen if you didn't have very much data in here. Or if you used what the book is calling the predictive distribution. You don't have any data. It really should be very diffused. I think that's a good thing to do. Any questions about that? Let's just look at example real quick. Set up some motivation. Let's imagine we're going to try to predict from a normal distribution. Example, let's say our xi's or iie coming from a normal with mean mu and variance sigma squared. And I'll let that be known just for now. So we've been graced with sigma squared in this analysis. So this is just an example, and you'd probably need to infer what sigma squared was. In a future homework, I have you do exactly that. We'll talk about some of the mechanics of that problem. So I've got all these data points, and I want to predict the future. Statistician's not going to say the future is 5. They're going to give you a distribution modeling your uncertainty about the future. So predict the future, and we'll call that x tilde, and that's just a random variable. So it's some dummy argument. Hypothetical value of the future. We're going to want to know what its distribution is. So the xi's come from a normal. Let's just write down some priors. I guess we just need one. So which prior would you pick for this problem? Say I've told you nothing about mu and sigma squared. You don't know anything about it. I just say I'm using a normal. Which prior? Yeah, maybe the flat one, right? So what properties would we get out of that? It is the reference prior. So that's a word that we know now, but we don't exactly know what it means. We know that in some sense, it's minimally impacting the analysis. So the likelihood has the most say in some sense. Less technically. It's shift and vary. So I get optimal coverage intervals. So if you do the same exercise using that prior that you did for the beta binomial thing, or at least you're going to do soon, you would find out that the intervals cover 95% of the time. There's no jigging and jagging. It works equally well for any value of mu, so it's uniform across that whole spectrum. So it has a uniform property. That's kind of nice. So everybody likes the normal distribution. It behaves well. No boundaries or anything like that. So we've got a few properties. So proportional 1, we kind of like those properties. If we knew something about mu, you might use it. I would be really weary if somebody used information about something without telling me where it all came from. So it really substantiated that. So what's our posterior distribution? And I'll leave the sigma squared in there just as notation. What does that become? Normal. What's the mean? X bar, kind of like that. And I'll do the last bit. Sigma squared over n. So we can try to do this sort of thing. So what we need to do to find the posterior distribution is work through this integral. We know what the sampling distribution is. It's normal. So let's just write it down, at least have all the notation on the board and see which integral we might want to solve. And if we have a little bit more endurance, we spend 25 minutes chiseling away at this thing. So it doesn't take too much more than that. But this would look like this. So pi mu given, oops, this is going to be the predictive distribution, x tilde given x, and I'll leave in notation that we know sigma squared. And usually, like, if I were taking tests or something like that, midterms, I like to remind myself of things, what I know in which layer of the problem, and so I try to come up with a notation that is a constant reminder to me. So I might want to remember that. Same thing that we had before. We're going to, of course, have mu. I'm going to, again, just be consistent, condition on sigma squared, but it's conditional in the whole analysis. It's being conditioned on. So I know that it's a fixed constant throughout everything. And then I'm going to have my posterior distribution. X sigma squared d. I'm going to integrate between negative infinity and infinity because that's where mu lives. And this thing is just going to be this integral. 1 over square root 2 pi sigma e to the minus 1/2 x tilde minus mu squared over sigma squared. And I'm going to multiply by the posterior distribution. 1 over square root 2 pi. I've got a sigma over root n that pops up there. E to the minus 1/2 x bar, so I'll say mu minus x bar squared over sigma squared over n d mu. So we'd have to do this integral. And the key to doing this integral is you do have to complete the square. So to work through it. We're not going to do that. We will look at a couple examples. I might humor you guys with the beta binomial. Maybe not the beta binomial. Maybe we can just write that one down today. That's not too hard. Maybe we'll do it with a Poisson distribution next week. Something like that. Introduce us to some new distributions. Okay, so of course you know how to solve this, hopefully, but you have to complete the square. Recognizing normalizing constants will help you. That same trick. If you didn't know that trick and you didn't realize this was a Gaussian distribution and what it was normalized by, you would need to use polar coordinates. I won't have you do that, but if you want to, if you're one of those that likes a good integral puzzle, you could work through that. Okay, we'll come back around to that integral next time. What do you think this distribution is? So what family do you think that lives in? I heard it, so I'll just write it down. So it's a normal. How can you tell? Yeah, it's going to be, you kind of know if you are going to complete the square, you're going to have some e term that's going to pop out, and it's going to slide through the integral, and it's going to involve this thing. So you can already see it. We're not integrating over x tilde here, so you can factorize out the e to the minus 1/2 x tilde right over here. You can't throw it away. It's not part of the normalizing constant. It doesn't belong in the integrand because you're not really integrating over it, but it's the random variable, so you don't get to toss that. So you can already see there's going to be an e to the minus x tilde squared in there, and so you can kind of imagine the rest of it is going to have the information about the mean and the variance in there once you complete the square. We'll come back and solidify that, but you can almost recognize what else would it be. So it's a normal. So what's the expectation in the variance? And that's a slightly harder question. And you might think you need to solve everything to do that, work through the integral. I'll give you another technique that's a little bit easier today. But let me just show you a computational approach. Let's say you had no idea how to solve this integral. And certainly for lots of distributions, that would be the case. So, in general, say you want, we'll go back to our old example, or our old notation, pi x tilde given x. I'm not really using pi as any special notation. I usually just denote my posteriors with pi. Fx tilde given theta, posterior distribution on theta, given x. D theta over everywhere. So say I didn't know how to solve this integral, but I knew how to sample from each distribution. So what I mean by that is I've got pi theta given x, the posterior distribution, It's a function over theta. And let's say it looked like this, some weird distribution. And so what I mean to sample from it is I can reach in here, let's say this interval right here, and I can grab values in that interval with frequency proportional to the area under the curve. I'll just write that down. Proportional to that area. And that's what sampling is. So there is a big presumption, how do you sample? But this is really the question that made Bayesians useful, is they figured out classes of techniques for sampling from arbitrary complex distributions. So before the 90s, this is a hard question. And so there's all kinds of techniques out there, variance reduction for doing Monte Carlo. Monte Carlo's slow. What happens? Computers speed up and we have more storage. And so people start pushing on the algorithmic development because now you can store everything. I remember the day where I had this brand new compact computer. It was really snazzy. I wanted to dual boot the thing. So I wanted to put Linux on it and have the native Windows operating machine. So the old school thing to do it. It sucks when you do that. So computer never really functions. Things don't cooperate, especially on a Windows machine. So modem didn't work back in the day of modems, things like that. But as soon as I did that, I wiped out all my RAM. And so solving an MCMC problem or a hard sampling problem would have been impossible on that computer. You guys already know, nowadays your phones can probably do this. So we'll be talking about techniques and how much space and storage they use, how much computation they use. In a nutshell, general algorithms that are flexible, that can handle very complicated distributions in general, they tend to work slower than algorithms that are tailored to do something fast on something simple. So that's true of all algorithms. This is probably the part that got me into being Bayesian, because I like to code. So back in the day. So I kind of like the algorithmics that it goes hand in hand with Bayesian statistics. We'll talk about that later. So we want to solve this integral. Right here. So what I'm going to do is I'm going to sample a heck of a lot of times from this distribution. Remember, my distribution looks something like that. And what I mean by that is I'm just going to come up with a histogram approximation of it by using a bunch of samples. So if I made a histogram and it had the same shape, my histogram is obviously normalized in some way. I just mean I've collected a lot of samples that look about like this curve. And if it looked like this right here, I'd probably think that's pretty. So I probably want to refine the histogram a little bit and make sure that it's got all the little curvy bits in there. So you sample a heck of a lot of times. I'm going to presume we know how to do this. So we want to come up with this weighted average right here. Here's how we're going to do it. I'll just write it down. So this is the Monte Carlo approximation for this. And this is plain Jane vanilla Monte Carlo, nothing fancy, because presumably I know how to sample from that distribution. So what I'm going to do to come up with the expectation, so this will be the Monte Carlo approximation for the expectation. That will look like this. F of x, and I'm just going to write this down, is I, right there, I'll call it x tilde I, given theta, let's just do the Monte Carlo approximation of this function, if you will, for our first step. I'll show you a couple layers to this. So this is just going to look like this. So theta, I'll call it I, right here. Not use the same letter that I used before. I'll call it k. So k is going to be samples from our posterior distribution. Let's call this theta k. It's going to come from our posterior. So what I mean by this when I write this down, theta k comes from our posterior. For each one of those that goes into the sum, I've reached into this distribution and I've plugged it off. And I plug it in. So that's what our notation means. So I'm going to do this some large number of times. I'll call it cap k. So something big. How big is big? When this thing settles down, it will be big enough. And then I'm going to normalize. I'm going to divide by k right here. So this is an average. So which average is it? I say it's exactly this thing. So as cap k goes off to infinity, they converge into each other. You can almost see that they're the same things. So this is sampling this function right here. This is the expected value, if you want to think about it that way. What's an expected value? Let's just remind us. Expectation of x is equal to x fx dx. So over the whole range of x. So that's what an expectation is. If I want an expectation of a function of x, then I just drop that function right there. And that's the same thing. So I just plug whatever the expectation is here. What am I doing? I'm averaging with respect to those weights. So what is this thing right here? This is an expectation with respect to that. So it's an expectation of some weirder function. So the sampling distribution. That's how we kind of motivated this from the beginning. So this is that expectation right here. I'm averaging over this function, and each one of these is uniformly weighted. So this is a uniform average in some sense. Let me ask a question. When I average this with respect to the posterior distribution, I'm taking an average of these things, but my weights are uniform. So it kind of looks a little bit different. So I'm uniformly sampling these things, but keep in mind, the posterior frequency, the frequency of these samples will be greater in these higher regions, so than over here. So how often am I going to get samples over in the tail? Well, it's going to be proportional to that area in that tail. How often am I going to get samples in this big mode right here? It's going to be proportional to that area. So the samples will appear more often in this sum because of the way we're sampling. We're sampling those theta k's from that distribution. So it does have that weight built in through the sampling. So it's a little different from like quadrature, if you know something like that, where you're just weighting by the interval length, but we end up cutting or sampling weights in there by sampling over theta. So when I see this integral, I actually see that. So I always think when I see a mathematical equation, how would I code it up? What is that thing? It is a process. And I try to think about it as a process. So this is going to give us this function right here. This would be pretty hard to express. So if you're trying to write that down, you've got all these functions. If you're trying to use your symbolic whatever in MATLAB, you'd have this long symbolic function. And so it'd be huge, it'd be difficult to play around with. So in Spirit you could do that, but most people don't do that. Instead what they're going to do is they're going to get samples for x tilde that represent this function right here. So I'll say as k in here goes to infinity, this converges. To pi x tilde given x, our posterior distribution, but that would be a pretty heinous function to write down and to work with. In Spirit, it's easy to recognize what's going on. What are we going to do to get samples from x? Here's the process. So Monte Carlo samples. From x tilde, I'll call it the whole thing, pi x tilde given x. This is a two-step process. So step one, we're going to get our theta k from our posterior distribution. So this is going to be exactly the same step that we performed. Our next step is going to be to condition on that theta k and get a new xk. I'm going to get that from this distribution, given theta k. This is going to be that value. I'm going to plug that directly in. So let me just say what I just wrote down. I'm going to plug off a value. I'm going to do this over and over again. So for k goes from 1 at k, we're just going to iterate over this. Now there's a presumption that I know how to sample from both of these functions perfectly. I call that a pi, but in my previous notation I was calling that an f. So these are just these two distributions that we're sampling from, but we're doing it hierarchically. And so I'm going to get a sample from theta, and then I'm going to get a sample from xk, and I'm going to plug this in. What am I really getting? I'm getting a joint sample of both of these. So I'm taking this is the conditional distribution. When I multiply the conditional distribution into that distribution, I get a joint distribution of theta and x tilde. Let me write that down. So this thing right here, this is fx tilde and theta given cap x. I don't need a cap x here. So you might be, if you're studying probability recently, you would say that's true if I was conditioning on the cap x in both places, then it would be conditioned here. But I'm going to make the argument I can just forget about that and it's exactly the same. Why is that true? So mathematically, if I'm going to multiply a conditional into its marginal distribution or conditional distribution, however you think about this, but I'm just going to think about fx tilde given theta, and if I did something like that, that's fx tilde and theta. It's the joint distribution. This is the same sort of thing, but we're conditioning on something. So if I condition there, I should condition here, and I should condition here. My claim is that x is independent. Why is it independent? Because this was an IID realization, and given knowledge of theta, previous x's don't teach you anything. You already know everything. Flustered? You almost need to experience it. Any questions? So this is independent because everything was IID. If this wasn't an independent function, if we weren't sampling independently, let's say it was Markovian or something like that, you'd have to build in that conditioning right here. So if you're working with a Kalman filter, or you're used to doing time series, you're probably familiar with that approach. We can look at that later in the class. So I'm sampling from theta from that distribution. You can think of this as the distribution on theta. Of course, it's conditioned on x. I'm plugging that thing in, and I'm popping out x tilde, conditional on it. What is that? That's a joint realization. So it's a joint sample from that distribution. So if I forget about these, as soon as I plug those in, and I just collect these, what I've done is integrated out theta. So what you're getting, you might be forming something like a matrix on your computer, storing it into a text file, and it would look like this. So theta 1, x tilde 1, theta 2, x tilde 2, theta 3, x tilde 3, all the way down. Theta cap k, x tilde cap. So these are joint samples. I can't scramble the order of these things. Like I can't pair that one up with that one and call it a joint sample because it came from a different iteration. That theta and x tilde are somehow related to each other. Now, if they were independent of each other, you could scramble them. But they're not independent of each other. Those thetas are driving the x's. And so here's the beauty of Monte Carlo sample. If I just got rid of this, the thetas, and I just looked at these, those would be my margins. So these right here are just these. Integral of, I'll call it fx tilde theta. I don't know if to use an f here or a pi. So you just decide. If I wanted to integrate over that, what is this thing if I integrate over theta? It's the exact same function over here. I've just written it its joint formulation. They're identical to each other. So I want to integrate that thing out. Right here, what I could do, Monte Carlo-wise, is just collect joint samples and throw away the thetas. And that's auto integration. That's Monte Carlo integration. So it couldn't be easier if you know how to sample from those distributions. If I wanted the thetas, I guess I could get those. These are posterior draws. So where did I get them from? I got them from here. So if I wanted the posterior draws, I could just look at those. If I wanted the forecasting draws, I would just look at those. So that's kind of nice. So think about what's happening here. I'm weighting the thetas by that and plugging it in. So how often are those thetas happening that I'm pairing with these x tildes? They're getting weighted by pi theta given x. And that's what this formula says to me. So this average equation is modeling the average over that. How are we averaging over the thetas in these steps? We're just getting it from its sampling frequency. And the same argument applies to the x tilde. You're getting those with their apparent sampling frequency. I can't draw just one histogram right here because this distribution is moving all over the place depending on which theta I plug in there. So for our example where theta is mu, it's recentering that distribution and it's flying all over the place. So I can collect a bath of samples here and then take that bath of samples and plug it in here and get another bath of samples out of this. But I need to be able to pair those thetas with those x's, x tildes. I'll have you code that up in the near future. So our example, back to normal, what I might do is I can get my mu's. I'm going to get it from our posterior distribution. I know what sigma squared is. This thing is just a normal on x bar given sigma squared over n. So I can sample a heck of a lot of times out of that thing. I can take those samples and I can plug them in to the forecasting distribution. X tilde k is going to come from f of x tilde given mu, and sigma squared is in there. And so this thing is just a normal centered at mu k. So I'm taking that in. That's mu k. That's this value. And then I've got sigma squared in here. So that's my inherent variance that I can never run away from in my prediction. Notice that if n is big, I can drive that variance way down. So if my samples in the first place, this cap x, is very large, this thing will be very tight, and I'll probably be sampling something close to the MLE, close to X bar. If n isn't very big, or the variance is huge in the first place, then the Bayesian is going to look different than plugging in the MLE, because they're going to be averaging over a lot of uncertainty. So this would be easy to code up. You could do it in 2 steps. Does everybody know how to sample from a normal distribution? You've all done it, I'm sure. So how do you do it? Yeah, you got R. So if you get like, you know, randin, that's at least the command in MATLAB. I don't know what it is on R off the top of my head. But random, parentheses, normal, you plug in the mean and the variance. Does anybody know what that algorithm is doing? So it gives you perfect draws. You don't have to wait for it to converge or anything like that. It gives you 2 normals for the price of 2 uniforms. And everybody uses the same algorithm. It's called the Box-Mueller algorithm. And if you want to train yourself on doing some trigonometric transformations, you can go and look at that algorithm. So it's kind of a cool thing. Maybe we could look at it in a review session if you guys were so inclined. Otherwise, look at the Wikipedia page. It's a fun transformation problem, transforming uniforms into normals. Okay, let's look at the Monte Carlo approximation for getting everything. If I wanted a Monte Carlo approximation of the mean, I could just take my samples at the end of the day, x tilde k, and I could divide by 1 over cap k. So k is going to go from 1 to cap k. And this empirical average is going to look very similar to this. X tilde given x. So if I didn't know how to do the integral and I knew how to sample from both layers, posterior distribution and the sampling function, in this case they're both normal. So if you know how to do one, you know how to do both of them. Then I could just average these samples. And that average would converge to this. Why does this average converge to that? There's all kinds of reasons. So why do averages of samples converge to the true average? The mean of the mean is the mean. So I like to think about that. It's the central limit theorem, the law of large numbers. I probably mean the strong law. So the weak law holds too. It adheres to this case right here because we're only talking about the expectations. It does it in the strongest form possible. So, and the samples are perfect. So it converges real quickly. So probably K doesn't even need to be that large, but I would still recommend make it something like 10,000 or 1,000,000 on your computer. So it's so fast and so cheap now, make sure those numbers are big in your Monte Carlo. How you want to check to see if they're big enough is you would do the whole thing over again and then compute that number. And if it was about the same within your tolerance, maybe 2 decimal places or something like that, you might be satisfied. I'd recommend you do it a couple times and make sure that you're consistent up to the same decimal point. So this is converging to a number, not a distribution. Of course, this is distributed in some fashion for small k. It's a CLT thing. Okay, we could do that. We could also compute the variance. X tilde given x. I could compute it like this. Same thing that you probably suspect. So this is just going to look like the sum of the xk tildes minus x bar tilde. That's terrible notation. But that just means it's the expectation of x tilde given x. It's this thing. So you're going to plug that thing in. So we'll do that. Let's give us some better notation. Expectation of x tilde given x. How are you going to approximate that? You're going to use this. you're going to plug that thing right in there. So you're not actually going to have this, you're going to have an approximation of that. So let me plug that in. Sum of the xk tilde 1 over cap k, k goes from 1 to cap k. So I've used the same index twice. I think it's okay, but I can call this a k prime if you wanted to. So k prime goes from 1 to cap k, 1 over cap k. And if you wanted to, square, and if you wanted to subtract off 1 right here, you could, if that was your estimate for variance. So if you do subtract off 1, and it's very different from my number, we should probably pause and think we don't have a lot of data. So I tend to like this estimate. This is the unbiased one. 1 over cap k minus 1. Now, this would be a pretty ridiculous calculation if everything was normal, because you could find the exact mean and the exact variance, so you'd probably want to write them down. You could get analytical forms of those. But for a complicated problem, you might do this. Just use the empirical forms. If I wanted some transformed expectation, let's say I have some function here, g, that doesn't change anything. I just put g in here and I have an expectation of a transform, and I just plug it in. No Jacobians, no derivatives required. I just transform directly. You don't need a Jacobian or a derivative because these are all discrete samples. So even though it's coming from a continuum, we have a discrete approximation for it. And when you transform PMFs, mass functions, no Jacobian, no stretching of the space. Everything is discrete. So you just transform directly. This is probably my favorite thing about Monte Carlo, is if I have the algorithm running and somebody changes the problem, it's a big transform, something super complicated, I don't have to do any math. I just go back to the code real quickly, I plug in that function, bada bing, bada boom, I wait 5 seconds, and I've got my new answer. So I kind of like that. So this could be presumably a very difficult thing to compute even for the normal example. Let's look at a couple forms. We'll come back and we'll pick up with these next time. But in general, these forms are true. So these are, and I'm just going to write down something generic right now. So we can just think about everything as a side. So I'll just go back to my old notation z, and I'll say I want the expectation of some random variable z. How do you do it? You solve that integral. There's another way you can do it. Sometimes this is useful if you have a hierarchical representation of your random variable. So this will look like this. Expectation of z given w. This is another random variable. So you have what's called the iterated expectation. So this expectation is over z given w, and this expectation is over w. So this is marginalizing out the w. And probably you haven't seen this since 1 page of your inference book if you don't work with hierarchical models, so it's probably useful to do a couple examples. Bayesians use these formulas pretty regularly. So there's also a formula that's similar for variance, and I'll just write it down, and we'll come back next time. We'll probably prove this one, but if you want to chisel away both of them over the weekend, maybe that's a good exercise. Or look in any standard inference probability book, and it'll have these proofs for you. So this is variance of z. If you have a hierarchical representation of this, you can write it down like this. Variance of z, variance of the expectation of z given w, plus the expectation of the variance of z given w. If you know how to apply these formulas, you can figure out what that expectation and variance is from our example in a pretty simple calculation. I want to come back and show you how to apply these formulas to posterior predictive distributions, how they work in general for hierarchical representations. But this would assume that Z was coming from some distribution FZ given W, and then I have a representation for W. W comes from some distribution on its space. And so I'm taking this W, I'm plugging it in here, and plucking off the Z. So that's a hierarchical model for modeling Z. What are you really doing? You're modeling a joint relationship with another random variable, and then just plucking off your Z. Same thing that we do in a posterior predictive distribution. So let's come back next time, prove this real quick. I'll let you guys prove this. I won't ask you on a test or a midterm to prove that. In your undergrad probability class, it wouldn't be uncommon to prove something like that, maybe even in grad school. But basically all you do is you show that the left and the right-hand sides are the same. So you work out both of them, and then after some simplification, you go, lo and behold, the left and the right side are the same. This looks more complicated than that, but this presumes that you can write down the marginal distribution for Z. And you might just have a conditional representation of it. And you might not want to work through that integral. But basically, both these operators right here are integral signs. Let's come back next time, look at that, apply it to our example, and then let's look at a couple other examples. See how good we are at recognizing what conjugate priors are, what the calculations would be, and then I'll probably do everything that we've done so far with the Poisson example. I'll probably be able to cut the time in half, so we'll look at what its posterior distribution is, properties of the priors, which prior is conjugate, so on and so forth, and then we'll work through the posterior predictive distribution. That's it for now. Have a great weekend, you guys.